Now let's go to another subtopic here, which is, we've considered an AC circuit in which we have two types of components, that is resistors and capacitors, resistors and inductors. Let's discuss an AC circuit that contains both inductor and capacitors. So we have RC series circuit. So now consider the AC circuit below. We have this AC circuit below. Here we have, of course, it has a potential difference and it also has a frequency, the source. So here we have both an inductor and a capacitor. So now I want you to remember that, okay, let me divide this into two. I want you to remember that when we discussed AC circuits containing only an inductor, we said in inductors the voltage leads the current by 90 degrees or pi over 2 radians. Now, if you're to use a vector diagram to illustrate this information, we have this, where the voltage in the inductor will lead the current in the inductor by 90 degrees. And of course, this will be true only if we take a direction in this way. So let's call this one diagram 1, vector diagram 1. Also, remember that in the capacitor, current leads voltage by 90 degrees or pi over 2 radian. That's what happens. And you can check this using an oscilloscope. You connect it to the circuit, and then you can find the phase angle between the voltage and as well as the current. So if you use a vector diagram to illustrate this, to explain or to illustrate this information like you did here, you're going to have something like this, when the current in the capacitor will lead the voltage in the capacitor by 90 degrees. And of course, again, this will be true only if you take your direction this way. So we call this vector diagram 2. Now, I want you to remember that these two components are connected in series. And in an electrical circuit, it doesn't matter whether it is a AC circuit or DC circuit, you have the same current passing through all of them. Which means when you set up the apparatus this way, and there's a current flowing through all of them, when you take your ammeter to measure the amount of current passing through this, and the amount of current passing through this, you find out that they're exactly the same. It will only be different if the two of them are connected in parallel. Something like this. That's when IL will be different from IC. You see, but in this case, when they're connected in series, you can be rest assured the same current will be passing through them. Now, since from experiment we can see that both IL and IC are equal in both magnitude and direction. It means that since this IL and IC are equal in both magnitude and direction. By the time we combine these two, these two diagrams together, we'll get something like this. Where this horizontal path is, we have IL slash IC, they're the same by the way. And here we have VL, and here we have VC. So we have 90 degrees here and 90 degrees here. So here we have, in this case, in this place, you see, what we have here is the same thing as what we have here. You see, now what we have here is the same thing as what we have here. You know, in this case, the current in the capacitor is leading the voltage by 90 degrees, and that's what you have here as well. The current in the capacitor is leading the voltage in the capacitor by the same 90 degrees. You see, and that means from this diagram 3 here, diagram 3 shows theoretically that the voltage in the inductor leads the voltage in the capacitor by 180 degrees. That's the phase angle between the voltage in the inductor and the voltage in the capacitor in an LC series circuit. You see, and when you do a practical on this, you find out that it's the same. When you compare the voltage over the inductor to the voltage over the capacitor, you'd find out that the phase difference between them is 180 degrees. You see, so now ignoring this horizontal vector here and take this one only, we have VL, VC. You can see that if you want to add up the two vectors together, vectors that are going in opposite direction, the total vector, that's the aggregate, the resultant vector, which is the voltage of the source, is actually the sum of these two. The voltage of the source of two vectors, sorry, the vector addition of two vectors oppositely directed to each other is the sum of the two. So we have VL plus VC. But you can see that VC is oppositely directed to VL. That means it carries a negative plus minus VC. It is oppositely directed to VL. So when you multiply these two signs, you get, therefore, V is equal to VL minus VC. We call this equation 1. You see, now if you use Ohm's law, remember that V is equal to IZ, VL is equal to IXL, and then VC is equal to IXC, which is capacitive reactance, inductive reactance. You see, now when you call this equation 2, when you substitute, or when you put equation 2 into equation 1, we're going to get something like this. So here we have we're going to have IZ is equal to IXL minus IXC. So we bring out a common factor, and then we have IZ is equal to I bracket XL minus XC. This I cancels this one out. Therefore, Z is equal to XL minus XC. So we call this one equation 4. Now, equation 4 gives the impedance. Equation 4 gives the impedance in an LC C series circuit. Yes. So in an AC circuit where you have the inductor and capacitor connected in series like you have here, the total impedance, the total reactance is the same thing as XL minus XC.